In mathematics, a polynomial is an expression consisting of variables and coefficients, that involves only the operations of addition, subtraction, multiplication, and non-negative integer exponents. An example of a polynomial of a single indeterminate, x, is x to a 4x plus 7, which is a quadratic polynomial. Polynomials appear in a wide variety of areas of mathematics and science. For example, they are used to form polynomial equations, which encode a wide range of problems, from elementary word problems to complicated problems in the sciences. They are used to define polynomial functions, which appear in settings ranging from basic chemistry and physics to economics and social science. They are used in calculus and numerical analysis to approximate other functions. In advanced mathematics, polynomials are used to construct polynomial rings and algebraic varieties, central concepts in algebra and algebraic geometry. Etymology: according to the Oxford English Dictionary, polynomial succeeded the term binomial, and was made simply by replacing the Latin root b with the Greek poly, which comes from the Greek word for many. The word polynomial was first used in the 17th century. Notation and terminology: the x occurring in a polynomial is commonly called either a variable or an indeterminate. When the polynomial is considered for itself, x is a fixed symbol which does not have any value. It is thus more correct to call it an indeterminate. However, when one considers the function defined by the polynomial, then x represents the argument of the function, and is therefore called a variable. Many authors use these two words indifferently, but this may be sometimes confusing and is not done in this article. It is a common convention to use uppercase letters for the indeterminates and the corresponding lowercase letters for the variables of the associated function. It may be confusing that a polynomial p in the indeterminate x may appear in the formulas either as p or as p, x. Normally, the name of the polynomial is p, not p, x. However, if it denotes a number, a variable, another polynomial, or, more generally any expression, then p, a, denotes, by convention, the result of substituting x by a and p. For example, the polynomial p defines the function. In particular, if a equals x, then the definition of p, a, implies. This equality allows writing let p, x, be a polynomial as a shorthand for let p be a polynomial in the indeterminate x. On the other hand, when it is not necessary to emphasize the name of the indeterminate, many formulas are much simpler and easier to read if the name, s, of the indeterminate, s, do not appear at each occurrence of a polynomial. Definition: a polynomial and a single indeterminate can be written in the form where are numbers, or more generally elements of a ring, and is a symbol which is called an indeterminate or, for historical reasons, a variable. The symbol does not represent any value, although the usual laws valid for arithmetic operations also apply to it. This can be expressed more concisely by using summation notation. That is, a polynomial can either be zero or can be written as the sum of a finite number of non-zero terms. Each term consists of the product of a number a called the coefficient of the term a and a finite number of indeterminates, raised to integer powers. The exponent on an indeterminate in a term is called the degree of that indeterminate in that term. The degree of the term is the sum of the degrees of the indeterminates in that term, and the degree of a polynomial is the largest degree of any one term with non-zero coefficient. Since x equals x1, the degree of an indeterminate without a written exponent is 1. A term and a polynomial with no indeterminates are called respectively a constant term and a constant polynomial. The degree of a constant term and of a non-zero constant polynomial is 0. The degree of the zero polynomial is not defined. For example, is a term. The coefficient is a 5, the indeterminates are x and y, the degree of x is 2, while the degree of y is 1. The degree of the entire term is the sum of the degrees of each indeterminate in it, so in this example the degree is 2 plus 1 equals 3. Forming a sum of several terms produces a polynomial. For example, the following is a polynomial. It consists of three terms: the first is degree 2, the second is degree 1, and the third is degree 0. Polynomials of small degree have been given specific names. A polynomial of degree 0 is a constant polynomial or simply a constant. Polynomials of degree 1, 2 or 3 are respectively linear polynomials, quadratic polynomials and cubic polynomials. For higher degrees the specific names are not commonly used, although quartic polynomial and quintic polynomial are sometimes used. The names for the degrees may be applied to the polynomial or to its terms. For example, in x2 plus 2x plus 1 the term 2x is a linear term in a quadratic polynomial. The polynomial 0, which may be considered to have no terms at all, is called the zero polynomial. Unlike other constant polynomials, its degree is not 0. Rather, the degree of the zero polynomial is either left explicitly undefined, or defined as negative. These conventions are useful when defining Euclidean division of polynomials. The zero polynomial is also unique in that it is the only polynomial having an infinite number of roots. In the case of polynomials in more than one indeterminate, a polynomial is called homogeneous of degree n if all its terms have degree n. For example, x3y2 plus 7x2y3 or 3x5 is homogeneous of degree 5. For more details, see homogeneous polynomial. The commutative law of addition can be used to rearrange terms into any preferred order. In polynomials with one indeterminate, the terms are usually ordered according to degree either in descending powers of x, with the term of largest degree first, or in ascending powers of x. The polynomial in the example above is written in descending powers of x. The first term has coefficient 3, indeterminate x, and exponent 2. In the second term, the coefficient is a 5. The third term is a constant. Since the degree of a non-zero polynomial is the largest degree of any one term, this polynomial has degree 2. Two terms with the same indeterminates raised to the same powers are called similar terms, or like terms, and they can be combined, using the distributive law, into a single term whose coefficient is the sum of the coefficients of the terms that were combined. It may happen that this makes the coefficient 0. Polynomials can be classified by the number of terms with non-zero coefficients, so that a one-term polynomial is called a monomial, a two-term polynomial is called a binomial, and so on. A polynomial in one indeterminate is called a univariate polynomial, a polynomial in more than one indeterminate is called a multivariate polynomial. These notions refer more to the kind of polynomials one is generally working with than to individual polynomials. For instance, when working with univariate polynomials one does not exclude constant polynomials, although strictly speaking constant polynomials do not contain any indeterminates at all. It is possible to further classify multivariate polynomials as bivariate, trivariate, and so on, according to the maximum number of indeterminates allowed. Again, so that the set of objects under consideration be closed under subtraction, a study of trivariate polynomials usually allows bivariate polynomials, and so on. It is common, also, to say simply polynomials in x, y, and z, listing the indeterminates allowed. The evaluation of a polynomial consists of substituting a numerical value to each indeterminate and carrying out the indicated multiplications and additions. For polynomials in one indeterminate, the evaluation is usually more efficient using the Horner scheme. Arithmetic of Polynomials. Polynomials can be added using the associative law of addition, possibly followed by reordering, and combining of like terms. For example, if, then, which can be simplified to work out the product of two polynomials into a sum of terms, the distributive law is repeatedly applied, which results in each term of one polynomial being multiplied by every term of the other. For example, if, then, which can be simplified to polynomial evaluation can be used to compute the remainder of polynomial division by a polynomial of degree 1, since the remainder of the division of f, x, by is f, a. See the polynomial remainder theorem. This is more efficient than the usual algorithm of division when the quotient is not needed. A sum of polynomials is a polynomial. A product of polynomials is a polynomial. A composition of two polynomials is a polynomial, which is obtained by substituting a variable of the first polynomial by the second polynomial. The derivative of the polynomial a(n)(xn plus a(1)(xn a1 plus a2x2 plus a1x plus a0 is the polynomial n(a)(n)(xn a1 plus a(1)(xn a2 plus 2a2x plus a1. If the set of the coefficients does not contain the integers, then k should be interpreted as the sum of arc with itself, k times. For example, over the integers modulo p, the derivative of the polynomial xp plus 1 is the polynomial 0. A primitive or antiderivative of the polynomial a(n)(xn plus a(1)(xn a1 plus a2x2 plus a1x plus a0 is the polynomial a(n)(xn plus 1 slash n plus 1 plus a(1)(xn n plus a2x3 slash 3 plus a1x2 slash 2 plus a0x plus c, where c is an arbitrary constant. For instance, the antiderivatives of x2 plus 1 have the form 1/3 x3 plus x plus c. As for the integers, two kinds of divisions are considered for the polynomials. The Euclidean division of polynomials that generalizes the Euclidean division of the integers. It results in two polynomials, a quotient and a remainder that are characterized by the following property of the polynomials: given two polynomials a and b such that b(a) permel 0, there exists a unique pair of polynomials, q, the quotient, and r, the remainder, such that a equals bq plus a and degree, r, degree, b. By hand as well as with a computer, this division can be computed by the polynomial long division algorithm. All polynomials with coefficients in a unique factorization domain also have a factored form in which the polynomial is written as a product of irreducible polynomials and a constant. This factored form is unique up to the order of the factors and their multiplication by an invertible constant. In the case of the field of complex numbers, the irreducible factors are linear. Over the real numbers, they have the degree either 1 or 2. Over the integers and the rational numbers, the irreducible factors may have any degree. For example, the factored form of is over the integers and the reals and over the complex numbers. The computation of the factored form, called factorization, is, in general, too difficult to be done by handwritten computation. However, there are efficient polynomial factorization algorithms that are available in most computer algebra systems. A formal quotient of polynomials, that is, an algebraic fraction where the numerator and denominator are polynomials, is called a rational expression, or rational fraction, and is not, in general, a polynomial. Division of a polynomial by a number, however, does yield another polynomial. For example, x3/12 is considered a valid term in a polynomial because it is equivalent to x3 and 1/12 is just a constant. When this expression is used as a term, its coefficient is therefore 1/12. For similar reasons, if complex coefficients are allowed, one may have a single term like x3. Even though it looks like it should be expanded to two terms, the complex number 2 plus 3i is one complex number, and is the coefficient of the term. The expression 1/x2 plus 1 is not a polynomial because it includes division by a non-constant polynomial. The expression is not a polynomial, because it contains an indeterminate used as exponent. Since subtraction can be replaced by addition of the opposite quantity, and since positive integer exponents can be replaced by repeated multiplication, all polynomials can be constructed from constants and indeterminates using only addition and multiplication. Polynomial functions. A polynomial function is a function that can be defined by evaluating a polynomial. A function f of one argument is called a polynomial function if it satisfies, for all arguments x, where n is a non-negative integer and a0, a1, a2, and are constant coefficients. For example, the function f, taking real numbers to real numbers, defined by is a polynomial function of one variable. Polynomial functions of multiple variables can also be defined, using polynomials and multiple indeterminates, as in. An example is also the function which, although it doesn't look like a polynomial, is a polynomial function on since for every from it is true that. Polynomial functions are a class of functions having many important properties. They are all continuous, smooth, entire, computable, etc. Graphs of polynomial functions. A polynomial function in one real variable can be represented by a graph. The graph of the zero polynomial f x equals 0 is the x-axis. The graph of a degree 0 polynomial f x equals ao, where ao permel 0, is a horizontal line with y-intercept ao. The graph of a degree 1 polynomial f x equals ao plus a1x, where a1 permel 0, is an oblique line with y-intercept ao and slope a1. The graph of a degree 2 polynomial f x equals ao plus a1x plus a2x2, where a2 permel 0, is a parabola. The graph of a degree 3 polynomial f x equals ao plus a1x plus a2x2 plus a3x3, where a3 permel 0, is a cubic curve. The graph of any polynomial with degree 2 or greater f x equals ao plus a1x plus a2x2 plus anxn, where an a permel 0 and n a permel 2n, is a continuous nonlinear curve. The graph of a non-constant polynomial always tends to infinity when the variable increases indefinitely. Polynomial graphs are analyzed in calculus using intercepts, slopes, concavity, and end behavior. Polynomial equations. A polynomial equation, also called algebraic equation, is an equation of the form. For example, is a polynomial equation. In case of a univariate polynomial equation, the variable is considered an unknown, and one seeks to find the possible values for which both members of the equation evaluate to the same value. A polynomial equation stands in contrast to a polynomial identity like xay equals x2ay2, where both expressions represent the same polynomial in different forms, and as a consequence any evaluation of both members gives a valid equality. In elementary algebra, methods such as the quadratic formula are given for solving all first-degree and second-degree polynomial equations in one variable. There are also formulas for the cubic and quartic equations. For higher degrees, the Abler-Euro-Ruffny theorem asserts that there cannot exist a general formula in radicals. However, root-finding algorithms may be used to find numerical approximations of the roots of a polynomial equation of any degree. The number of real solutions of a polynomial equation with real coefficients may not exceed the degree, and equals the degree when the complex solutions are counted with their multiplicity. This fact is called the fundamental theorem of algebra. Solving polynomial equations. Every polynomial p in x corresponds to a function, f x equals p, called the polynomial function of p. The equation in x setting f x equals 0 is the polynomial equation corresponding to p. The solutions of this equation are called the roots of the polynomial. They are the zeros of the function f. A number a is a root of p if and only if the polynomial xaa divides p. It may happen that xaa divides p more than once. If 2 divides p, then a is called a multiple root of p, and otherwise a is called a simple root of p. If p is a non-zero polynomial, there is a highest power m such that m divides p, which is called the multiplicity of the root in p. When p is the zero polynomial, the corresponding polynomial equation is trivial, and this case is usually excluded when considering roots. With the above definitions, every number would be a root of the zero polynomial, with undefined multiplicity. With this exception made, the number of roots of p, even counted with their respective multiplicities, cannot exceed the degree of p. The relation between the roots of a polynomial and its coefficients is described by varieties formulas. Some polynomials, such as x2 plus 1, do not have any roots among the real numbers. If, however, the set of allowed candidates is expanded to the complex numbers, every non-constant polynomial has at least one root. This is the fundamental theorem of algebra. By successively dividing out factors xaa, one sees that any polynomial with complex coefficients can be written as a constant times a product of such polynomial factors of degree 1. As a consequence, the number of roots counted with their multiplicities is exactly equal to the degree of the polynomial. There is a difference between approximating roots and finding exact expressions for roots. Formulas for expressing the roots of polynomials of degree 2 in terms of square roots have been known since ancient times, and for polynomials of degree 3 or 4 similar formulas were found in the 16th century. But formulas for degree 5 eluded researchers. In 1824, Niels Henrik Abel proved the striking result that there can be no general formula, involving only arithmetic operations and radicals, that expresses the roots of a polynomial of degree 5 or greater in terms of its coefficients. In 1830, a permalvarist Galois, studying the permutations of the roots of a polynomial, extended the Abler-Euro-Ruffny theorem by showing that, given a polynomial equation, one may decide if it is solvable by radicals, and, if it is, solve it. This result marked the start of Galois theory and group theory, two important branches of modern mathematics. Galois himself noted that the computations implied by his method were impracticable. Nevertheless, formulas for solvable equations of degrees 5 and 6 have been published. Numerical approximations of roots of polynomial equations in one are known as easily done on a computer by the Jenkinson-Traub method, Laguerre's method, Duranda-Kerner method, or by some other root-finding algorithm. For polynomials in more than one indeterminate, the notion of root does not exist, and there are usually infinitely many combinations of values for the variables for which the polynomial function takes the value 0. However, for certain sets of such polynomials it may happen that for only finitely many combinations all polynomial functions take the value 0. For a set of polynomial equations in several unknowns, there are algorithms to decide if they have a finite number of complex solutions. If the number of solutions is finite, there are algorithms to compute the solutions. The methods underlying these algorithms are described in the article Systems of Polynomial Equations. The special case where all the polynomials are of degree 1 is called a system of linear equations, for which another range of different solution methods exist, including the classical Gaussian elimination. Polynomials associated to other objects, calculus. The simple structure of polynomial functions makes them quite useful in analyzing general functions using polynomial approximations. An important example in calculus is Taylor's theorem, which roughly states that every differentiable function locally looks like a polynomial function, and the Stoney-Weierstrass theorem, which states that every continuous function defined on a compact interval of the real axis can be approximated on the whole interval as closely as desired by a polynomial function. Calculating derivatives and integrals of polynomial functions is particularly simple. For the polynomial function, the derivative with respect to x is, and the indefinite integral is. Abstract algebra. In abstract algebra, one distinguishes between polynomials and polynomial functions. A polynomial f in one indeterminate x over a ring R is defined as a formal expression of the form, where n is a natural number, the coefficients a0, and are elements of R, and x is a formal symbol, whose powers I are just placeholders for the corresponding coefficients I, so that the given formal expression is just a way to encode the sequence, where there is an n such that I equals 0 for all I, n. Two polynomials sharing the same value of n are considered equal if and only if the sequences of their coefficients are equal. Furthermore, any polynomial is equal to any polynomial with greater value of n obtained from it by adding terms in front whose coefficient is 0. These polynomials can be added by simply adding corresponding coefficients. Thus each polynomial is actually equal to the sum of the terms used in its formal expression, If such a term is interpreted as a polynomial that has zero coefficients at all powers of x other than xi, then to define multiplication, it suffices by the distributive law to describe the product of any two such terms, which is given by the rule AA for all elements A, B of the ring R and all natural numbers K and L. Thus the set of all polynomials with coefficients in the ring R forms itself a ring, the ring of polynomials over R, which is denoted by R, X. The map from R to R, X, sending R to Rxo is an injective homomorphism of rings, by which R is viewed as a subring of R, X. If R is commutative, then R, X, is an algebra over R. One can think of the ring R, X, as arising from R by adding one new element X to R, and extending in a minimal way to a ring in which X satisfies no other relations than the obligatory ones, plus commutation with all elements of R. To do this, one must add all powers of X and their linear combinations as well. Formation of the polynomial ring, together with forming factorings by factoring out ideals, are important tools for constructing new rings out of known ones. For instance, the ring of complex numbers, which can be constructed from the polynomial ring R, X, over the real numbers by factoring out the ideal of multiples of the polynomial x2 plus 1. Another example is the construction of finite fields, which proceeds similarly, starting out with a field of integers modulo some prime number as the coefficient ring R. If R is commutative, then one can associate to every polynomial P in R, X, a polynomial function f with domain and range equal to R. One obtains the value f, R, by substitution of the value R for the symbol x in P. One reason to distinguish between polynomials and polynomial functions is that over some rings different polynomials may give rise to the same polynomial function. This is not the case when R is the real or complex numbers, whence the two concepts are not always distinguished in analysis. An even more important reason to distinguish between polynomials and polynomial functions is that many operations on polynomials require looking at what a polynomial is composed of as an expression rather than evaluating it at some constant value for x, divisibility. In commutative algebra, one major focus of study is divisibility among polynomials. If R is an integral domain and f and g are polynomials in R, X, it is said that f divides g or f is a divisor of g if there exists a polynomial q in R, X, such that fq equals g. One can show that every zero gives rise to a linear divisor, or more formally, if f is a polynomial in R, X, and R is an element of A such that f, R, equals 0, then the polynomial divides f. The converse is also true. The quotient can be computed using the polynomial long division. If f is a field and f and g are polynomials in f, X, with g a permel 0, then there exist unique polynomials q and r in f, X, with and such that the degree of r is smaller than the degree of g. The polynomials q and r are uniquely determined by f and g. This is called Euclidean division, division with remainder or polynomial long division, and shows that the ring f, X, is a Euclidean domain. Analogously, prime polynomials can be defined as non-zero polynomials which cannot be factorized into the product of two non-constant polynomials. In the case of coefficients in a ring, non-constant must be replaced by non-constant or non-unit. Any polynomial may be decomposed into the product of an invertible constant by a product of irreducible polynomials. If the coefficients belong to a field or a unique factorization domain, this decomposition is unique up to the order of the factors and the multiplication of any non-unit factor by a unit. When the coefficients belong to integers, rational numbers or a finite field, there are algorithms to test irreducibility and to compute the factorization into irreducible polynomials. These algorithms are not practicable for handwritten computation, but are available in any computer algebra system. Eisenstein's criterion can also be used in some cases to determine irreducibility. Other applications. Polynomials serve to approximate other functions, such as the use of splines. Polynomials are frequently used to encode information about some other object. The characteristic polynomial of a matrix or linear operator contains information about the operator's eigenvalues. The minimal polynomial of an algebraic element records the simplest algebraic relation satisfied by that element. The chromatic polynomial of a graph counts the number of proper colorings of that graph. The term polynomial, as an adjective, can also be used for quantities or functions that can be written in polynomial form. For example, in computational complexity theory the phrase polynomial time means that the time it takes to complete an algorithm is bounded by a polynomial function of some variable, such as the size of the input. Extensions of the concept of a polynomial, rings of polynomials in a finite number of variables are of fundamental importance in algebraic geometry, which studies the simultaneous zero sets of several such multivariate polynomials. These rings can alternatively be constructed by repeating the construction of univariate polynomials with this coefficient ring another ring of polynomials, thus the ring R, X, Y, of polynomials in X and Y can be viewed as the ring, Y, of polynomials in Y with its coefficients polynomials in X, or as the ring, X, of polynomials in X with its coefficients polynomials in Y. These identifications are compatible with arithmetic operations, but some notions such as degree or whether a polynomial is considered monic can change between these points of view. One can construct rings of polynomials in infinitely many indeterminates, but since polynomials are expressions, any individual polynomial can only contain finitely many indeterminates. A bivariate polynomial where the second variable is substituted by an exponential function applied to the first variable, for example p, x, x, may be called an exponential polynomial. Laurent polynomials are like polynomials, but allow negative powers of the variable, s, to occur. Quotients of polynomials are called rational expressions, and functions that evaluate rational expressions are called rational functions. Rational fractions are formal quotients of polynomials. The rational function defined by a rational fraction is the quotient of the polynomial functions defined by the numerator and the denominator of the rational fraction. The rational fractions contain the Laurent polynomials, but do not limit denominators to powers of an indeterminate. While polynomial functions are defined for all values of the variables, a rational function is defined only for the values of the variables for which the denominator is not null. A rational function produces rational output for any rational input for which it is defined. This is not true of other functions such as trigonometric functions, logarithms and exponential functions. Formal power series are like polynomials, but allow infinitely many non-zero terms to occur, so that they do not have finite degree. Unlike polynomials, they cannot in general be explicitly and fully written down, but the rules for manipulating their terms are the same as for polynomials. History, determining the roots of polynomials, or solving algebraic equations, is among the oldest problems in mathematics. However, the elegant and practical notation we use today only developed beginning in the 15th century. Before that, equations were written out in words. For example, an algebra problem from the Chinese arithmetic in 9 sections, circa 200 BCE, begins 3 sheaves of good crop, 2 sheaves of mediocre crop, and 1 sheaf of bad crop are sold for 29 do. We would write 3za plus a2ya plus az equals a29. History of the notation. The earliest known use of the equal sign is in Robert Record's The Whetstone of Wit, 1557. The signs plus for addition, are for subtraction, and the use of a letter for an unknown appear in Michael Stieffel's Arithmetica Integra, 1544. Riener copyright Descartes, in La Gare copyrightometry, 1637, introduced the concept of the graph of a polynomial equation. He popularized the use of letters from the beginning of the alphabet to denote constants and letters from the end of the alphabet to denote variables, as can be seen above, in the general formula for a polynomial in one variable, where the a's denote constants and x denotes a variable. Descartes introduced the use of superscripts to denote exponents as well. See also, Lil's method, list of polynomial topics, polynomials on vector spaces, power series, notes. References. External links: Haswinkel, Michiel, ed., Polynomial, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4. Euler's work on imaginary roots of polynomials, Weierstein, Eric W., Polynomial, MathWorld.